Hi everyone. I'm going to talk to you today about velocity dependent forces, or about a specific velocity dependent force, and the types of expressions that come from, well, a situation, or can come from a situation like this. This is a special one where we're modeling a drag force whose magnitude varies with speed via the expression drag forces. That's a lowercase beta constant, a constant that makes the numbers work out and the units work out. Excuse me. So we're going to find how fast this object moves as a function of time. The object's velocity is a function of time. And we're going to consider only the horizontal component of the object's motion. And the reason we do that is because it quite literally makes the calculus a little bit simpler. Spoiler alert, we're going to have to do some calculus to solve this problem. So here's an object, and it's initially moving this way at a speed let's call v naught. And, well, the nature of drag forces, resistive forces, is that they are akin to friction forces. Or friction force maybe is a resistive force, but this drag force, Fd, looks like that. Now you'll notice that velocity is a vector, drag force is a vector, and they point in opposite directions. So we're going to have to deal with that later, but notice that I've said the magnitude of the drag force has this size, beta times velocity. All right, maybe we'll just deal with it now. The way we deal with that is that if this is the positive direction, because why not, then drag force points in the negative direction. Right? So we'll apply that later. So here's what we'll do. We're going to start with a net F, right, and apply Newton's second law. So basically this says that the net force is Fd. Okay, and well, the drag force can be modeled in our situation here as beta times the velocity is ma. Now, here's where we have to take into account that, well, that Newton's second law is a vector expression, and what we have here is a velocity that points in the positive direction and an acceleration via this drag force that points in the negative direction. So I'm going to say that the acceleration is negative, or the really net force is negative b times v. All right, what this says is that acceleration vector and velocity vector point in opposite directions. Okay, and this acceleration is negative if this is the positive direction. Okay, I understand it might look like, well, aren't you making the velocity negative? No, what I'm saying is pick a number for velocity. Acceleration is negative blah, blah, blah. Okay, so it's, even though I put the negative here, I'm not saying the velocity is negative, I'm saying the acceleration is. So, what now? We want velocity as a function of time. Well, here's what we have to recognize. We have to recognize that acceleration, by definition, is the time rate of change of velocity. And what this says is that the rate of change of velocity depends on the velocity. And that, for that reason, it makes this a difficult, well, mathematically challenging expression to write for velocity. Okay, so here's how we do it. Well, we're going to have to get everything that has to do with v on one side of an equation and everything else somewhere else. Now, we don't have to do that, but that's what we're going to do. We certainly have to get everything that has to do with v on one side of an equation. We can leave other stuff with it if we choose. I'm going to only get the v stuff and, well, only the v stuff on one side and put everything else somewhere else. So here's how we do this. Well, this dv I want to leave by itself. So I'm going to multiply both sides by dt. I'm also going to divide both sides by the mass. And what we get is negative bv over m dt is dv. and divide both sides by v. And so we get this expression, negative v beta over m dt is 1 over v dv. Come on, I just want it to look nice. Can't you just, there you go, good. Okay, so, well, I mean, this really is a differential equation. And what we've done is use this technique, separation of variables, where we can, turn the differential into, a situation where we can integrate both sides to solve this differential equation. So what we can do now, as we said, is integrate both sides. The left side with respect to t, the right side with respect to v, and that will give us get us closer to our expression for velocity as a function of time. Now what we can do here is we can really talk about what are limits of integration. All right, we're going to say that, well, at time 0, this object has a velocity we called v0. And then at some time t, there is some velocity, which I'll write like that just so it looks different than, quote, plain old v. We're looking for velocity as a function of time. Okay, so the left side is a fairly trivial integral, and the reason is, well, this is a number. Beta is a constant. The object has a mass m, so all we're really doing on the left side is integrating, watch this, we can yank out the beta over m. We're integrating dt. All right, so I'll handle this part by itself. Let me move this part over here. So that's negative beta over m times t evaluated from 0 to t. And this is redundant for some of you. Maybe you recognize that this is basically, evaluate t at t and subtract evaluate t at 0. That's t minus 0. So this is, this left side evaluates to negative negative beta t over m. All right. The right side is not trivial. Okay. The right side, you have to, in my shoes, you have to know that the integral 1 over x dx is, I don't want to say by definition, but it is the natural log of x. Why is that? Well, that's a subject for a different lecture. So I'm going to apply that fact and say this is the natural log of x evaluated from v0 to v as a function of t, right? Which means, well, we evaluate at the top and we subtract when we evaluate at the bottom. Now, for those of you that know your properties of natural logs, you know that this is the natural log of v as a function of time over v0. So that's what we end up with on the right side. So this stuff goes back down here, and this is equal to natural log of v as a function of time over v0. Now, what we want to do is isolate v as a function of t. So how do we do that? Well, we got to get rid of this natural log thing, and the way we do that is we take both sides and we raise them. Well, each side gets raised. Is that how you say it? Each side, we raise each side. I don't even know how you say it, but you do e to the each side. Because some of you know that, for example, e to the natural log of x is x. Or the natural log of e to the x is x. So we can now leave our left side alone and say we have e to the negative beta t over m equals v as a function of time, or v naught, or I'll switch sides because that's the way we're used to saying things. V as a function of t is v naught e to the negative beta t over m. So v does vary with time via this exponential relationship. Okay? And so what can we take from this, or what does this show us or tell us? Well, if we were to plot velocity as a function of time, this says that, well, for example, v naught, v at time 0, is v e to the negative v times 0, beta times 0 over m. Well, that's v naught e to the 0. That's v naught times 1. Yeah, okay, so v naught, well, there's a v naught, right? V of, sure, that, I mean, it better darn well be that at time 0, this thing has velocity v naught, because that's what we said, right? We said that right here. This agrees with that statement. And then what does this function look like? Well, I mean, you could plug in values of, make up values of b and t and m, but the short story is what this does is this starts with a decay and then asymptotes at velocity 0. It never reaches velocity 0, right? As the limit, as t approaches infinity, of negative beta t over m, that approaches 0. You'll have to forgive me, I don't know what I just said. I just paused because my children are tearing the house apart. So I think what I'm getting at is this function approaches 0, so the velocity approaches 0 as time gets really big, but it never technically gets there. And why is that? Let's think about what happens as time goes on. So, early on, what we have is a big velocity and a big force, right? Later, we have a smaller velocity, and so therefore a smaller force. Eventually, we have, a really small velocity, and so a really small force. Eventually, the velocity is almost infinitely small. Is that a word? I don't know. Is that a phrase? The velocity is tiny, 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 which means the force that's slowing it down is tiny, tiny, tiny. So it slows down super slowly. The slower it gets, the slower it slows down. That means it never really gets to a speed of 0, but the velocity approaches 0. Okay? Yeah, so that's a pretty cool application of a neat idea or a neat mathematical model where we say that acceleration, really force, but therefore acceleration varies linearly with v, which is to say, when I say acceleration varies linearly with v, that the rate of change of a function is dependent on the function, on the value of the function, and in particular, and is opposite of. That's going to lead us, there are lots of other ways you'll see this happen in nature, in electronics, for sure, where this ends up as an exponential decay function. Okay, we could also, from this, because why not, what's neat to look at is there's a couple different ways to look at the acceleration, and in particular we could say, well, what is acceleration as a function of time? Well, by definition, it's the rate of change of velocity. So if we want to find this object's acceleration, we can differentiate with respect to time the velocity function, v naught e to the negative beta t over m, which says we're really differentiating v naught is a number, so we're really differentiating the e to the negative bt over m. And there's a name for it, right? I don't know if it's the chain rule or the power rule or whatever it is. Here's what we do first. We have to know, first we differentiate the exponential function. And the thing about exponential functions, especially exponential functions with Euler's number, the special thing about those is that the derivative of the function is the function itself, e to the negative bt over m. Right, that's what's special about Euler's number. Exponential functions, right? Exponential functions have, yeah, I don't know, equals y is a function of x equals a raised to the x. That's an exponential function, right? Where the exponent is the variable. Exponential functions, right, start like here at 1, right? Here's y, here's x. So, you know, if x is 0, a to the 0 is 1. And so based on what a is, the function might go like this, or go like this, or go like this, or go like this. Ours happened to be, our x was negative. That's why we got a decaying function. But let's just talk about positive functions. So the neat thing about Euler's number, this number e, that's an actual number. It's not a integer, or I don't know the correct terminology for, it's one of those numbers that has an infinite number of decimal places, probably. The neat thing about that number is when you take y equals e to the x, the thing with that function is it looks, I don't know, say like that. Here's y, here's x. Well, you take a value of x right here. Let's call this value instead, I don't know, r, right? Right here, the slope of that function is e to the r. Okay, so the value of this function, right here, is e to the r. Right? Y equals e to the x. So when x is r, the value of the function is e to the r. The interesting thing, the definitional thing about Euler's number is that not only is the value of the function e to the r, the slope of the function is also e to the r. And that's, you know, you can imagine if this curve had a different shape, right, and did this and, you know, curved up, this function grew more rapidly, well, the slope wouldn't be the same as, the slope, you know, wouldn't happen to be the same as the value of the function. So that's what makes Euler's number. Pretty cool. What we, but that's the calculus stuff. Now back to the physics stuff, but it's still calculus stuff. What we have not done is we have not differentiated the exponent itself with respect to time, which we are required to do. And so when we do that, we differentiate negative bt to the m dt, and we get negative b over m. So that's our acceleration function. Acceleration as a function of time is negative b v naught over m e to the negative bt over m. All right, so what's that function look like? Well, that function looks, now first of all, let me do this. Let me see if I can. Yeah, I'll do it later. So this function looks like this. Here's t, here's a. Notice that all the a's are negative. At time 0, a naught, a at time 0 is negative bv naught over m e to the 0. So it's that. So that's this, negative bv naught over m. And this function does this. Asymptotes at 0, never gets there. I was pretty good. What did I erase? asymptotes at 0, never, that's better. It never gets there. And, well, remember let's see, if we want to know now's the time where I want to do this. Let me see if I can grab this stuff. And copy. Oh, not that. Undo, sir. Copy. Down here, let's beat it. Paste. Yes. Stop it. Note, folks, that our velocity function is in pink. Our acceleration function is in green. Stop it. And early on, say like here, well, immediately, right, the slope of this is big, and negative. Well, the slope is the acceleration. Look, the acceleration is big and negative. Later, the slope is still negative, but not as big, and the acceleration is still negative, not as big. And eventually, the slope gets really close to 0, but still negative. Yep, the acceleration gets really close to negative and still 0. So that shows a nice agreement. Yes? Yes. What's also nice to note is that if you look way back to here, that's a Newton's second law statement. I'm going to bring that down to here and say that negative beta v is ma. Well, guess what? Velocity is time dependent. So is a. Oops. And so, well, this says that a of t is negative b over mv of t. And what was our velocity function? Our velocity function was here. It says that a of t is negative beta over m v naught e to the negative beta t over m. And that agrees with our differentiation of the velocity function. This way sure is, quote, easier, but it's nice that they agree with each other. They better darn well agree with each other. All right, so yeah, this is a case like many other cases in nature, in physics, where we see, again, the rate of change of a function proportional to the function itself, the value of the function, but with an, quote, opposite in there, a, quote, negative in there. Okay, and those situations yield exponential decay results, or exponential functions like these. All right, you'll see them more and more as you continue along your path in physics. But this is a good start. Thanks, folks.